Welcome back to the Deep Dive. Today, we're going to be diving into the world of data-intensive applications.
Awesome.
These are things like the apps on your phone,
Yeah.
the websites you visit. We're using Martin Kleppmann's book, Designing Data-Intensive Applications,
Yeah.
as our guide for the deep dive.
It is, yeah. It's a fascinating area, especially now that we're generating and relying on data more than ever before.
Right.
And this book is a fantastic resource because it helps us understand not just how these systems work, but also why certain design choices are made.
Right. And one of the first things that really jumped out at me was this whole idea of the shift from compute-intensive to data-intensive applications.
Yeah.
Can you unpack that a bit? What's changed?
Sure. Yeah, it's a fundamental shift in how we think about software.
Okay.
In the past, the focus was on raw processing power.
Okay.
Like how fast can your CPU crunch numbers?
Yeah.
But now, the bottleneck isn't really the CPU anymore. It's the data itself. We're dealing with these massive data sets, complex relationships, and data that's just constantly changing.
So it's less about the horsepower and more about managing the flow of information, right?
Exactly. And that's where data systems come in.
Okay.
Things like databases, caches, search indexes.
Yeah.
They're the backbone of these applications.
Okay.
They provide ways to store, retrieve, and process information efficiently.
That makes sense.
And what's interesting is that building these applications is no longer about just picking one tool.
Yeah.
It's about understanding how different tools can work together.
Yeah.
It's like being an architect, like designing the infrastructure to handle this constant flow of data.
Okay, I'm starting to see the bigger picture.
Yeah.
But with all of this data flying around, how do we ensure that these systems are reliable?
That's a great question.
Like, what does working correctly even mean in this context?
That's more nuanced than you might think. It's not just about the system never failing.
Right.
It's about meeting user expectations.
Okay.
For example, a social media site might be designed to tolerate the occasional brief outage.
Right.
But an online banking system needs to be much more robust.
Of course, yeah.
Right.
So reliability is relative. It depends on what the system is actually designed to do.
Precisely.
Yeah.
And it also involves things like performance under heavy load
and
maintaining security.
Right.
But a core aspect of reliability is fault tolerance.
Okay.
The ability to keep working even when things go wrong.
That makes sense, right?
Yeah.
No system is perfect, so you need to plan for failures.
Absolutely.
The book talks about 3 types of fault.
Yeah.
Hardware, software, and human error.
Yeah.
Let's start with hardware. What kind of hardware failures are we talking about here?
Hardware failures are more common than you might think.
Okay.
Especially in large data centers.
Oh, wow.
Hard drives can crash, RAM can fail, power outages can happen.
Right.
It's not a matter of if, but when.
So how do these systems deal with those inevitable oh no moments?
Well, redundancy is key.
Okay.
RAID configurations for disks, dual power supplies, regular backups.
Right.
These are all critical.
Yeah.
Think of it like having a spare tire in your car.
Okay.
You might not need it often,
Yeah.
but when you do, you're really glad you have it.
That's a great analogy.
Thanks.
But as these systems grow and handle more and more data, wouldn't just relying solely on hardware redundancy become difficult?
You're right. As data volumes and computing demands increase,
Yeah.
there's a shift towards software fault tolerance techniques.
Okay.
It's more efficient to design systems that can tolerate individual machine failures without disrupting the entire service.
So it's about building resilience into the software itself.
Exactly.
Can you give an example of that?
Sure. Imagine a system with multiple servers. If one server fails, the software can automatically redirect traffic to the remaining servers, ensuring that users experience minimal disruption.
Right.
This also allows for things like rolling upgrades, where you can update the system piece by piece without taking everything offline.
That's pretty impressive.
It is.
Okay, let's move on to the second type of fault, software errors. These seem a bit trickier to anticipate.
They can be, yeah. Software errors are often systematic, stemming from bugs in the code, runaway processes, consuming all the resources, or dependencies between services that fail.
Yeah.
These errors can be difficult to predict.
Yeah.
Because they might lurk undetected for a long time before causing a major issue.
It sounds like a ticking time bomb.
Yeah.
How do you even begin to address something so unpredictable?
It's a multi-layered approach. Thorough testing is crucial.
Okay.
Testing individual components, how they work together, even simulating real-world scenarios.
Yeah.
Another important technique is process isolation.
Okay.
This involves running different parts of the application in separate environments.
Okay.
So that if one part crashes, it doesn't take down the entire system.
So it's all about containment.
Yeah.
Right. Preventing one small error from cascading into a major outage.
Great.
Okay. Now, the last category, and perhaps the most relatable, is human error.
Of course.
We all make mistakes.
We do.
But I imagine the stakes are much higher in this context.
Absolutely. In the world of data-intensive applications, even small mistakes can have big consequences.
Oh, wow.
A simple configuration error, accidentally deleting data, or deploying buggy code, can lead to service disruptions or data loss.
All right. So how do you design systems that are resilient to our own human fallibility?
Yeah.
What are some safeguards that can be put in place?
Well, it's all about building systems that are forgiving.
Okay.
One strategy is to minimize opportunities for error in the first place.
Okay.
This might involve using intuitive interfaces, clear documentation, or built-in checks that prevent accidental data deletion.
So kind of like training wheels for engineers.
Yeah.
A safe space to tinker and learn.
Exactly. It's also crucial to have robust testing procedures at every stage.
Okay.
Unit tests for individual components.
Right.
Integration tests for how those components interact.
Yeah.
And even manual testing to catch those edge cases.
Makes sense.
And of course, having quick and easy recovery mechanisms like fast rollbacks or gradual deployments can significantly limit the impact of any errors that do slip through.
It's like having a safety net.
Yeah.
You hope you never need it, but it's reassuring to know it's there.
Right.
This whole discussion about reliability makes me wonder, how critical is it for everyday applications?
Yeah.
Is it something that only mission-critical systems need to worry about?
Reliability is essential for any application that people depend on, whether it's a business application where downtime means lost productivity and revenue, or a consumer app where data loss could be devastating for users.
Yeah.
I think we have a responsibility to build systems that are dependable.
It's about building trust with users.
Exactly.
They need to know their data is safe and the application will work as expected.
Right.
Okay, let's shift gears and talk about scalability.
Sure.
Even if a system is running smoothly today, how can we ensure it can handle growth in the future?
Well, scalability is all about how a system adapts to increased load.
Okay.
It's not just a matter of whether it can handle more.
Right.
It's about understanding how performance changes as the load grows and having strategies to address those changes.
So it's like planning for a growing family.
Exactly.
You need a bigger house and more resources to keep everyone happy.
I like that. Yeah.
But how do you even begin to measure the load on a system?
Right.
There seem to be so many variables involved.
You're right. It's not always straightforward. We use load parameters to quantify the demand on a system.
Okay.
For a web server, it might be requests per second.
Right.
For a database, it could be the ratio of reads to writes.
Yeah.
The key is to identify the parameters that are most relevant to the system's performance bottlenecks.
Okay.
The parts that are likely to struggle under heavy load.
Makes sense. So once you've identified those key parameters, how do you actually measure the system's performance?
That's where performance metrics come in.
Okay.
For batch processing systems, throughput is important.
Okay.
How much data can be processed per second.
Yeah.
But for online systems, where users are waiting for a response, response time is usually the more critical metric.
And ideally, you want those response times to be as quick as possible, right?
Absolutely. But it's important to remember that response time isn't just a single number. It's a distribution.
Okay.
Some requests will be faster than others due to factors like network latency, background processes, or even mechanical vibrations in the server rack.
Wow.
Crazy, right?
So there's always going to be some variation, even if you send the same request multiple times.
Exactly. That's why we use percentiles to understand the distribution of response times.
Right.
Instead of just looking at the average, which can be skewed by outliers,
okay,
we look at percentiles like the median, the P50, the 95th percentile, the P95, and even the 99.9th percentile, or P999.
Wow.
This tells us what percentage of requests are handled within a certain time frame.
So, for example, if the 95th percentile response time is 1 second, that means 95% of requests are handled in under a second.
Right.
but 5% might take longer.
Exactly.
And those slower requests, those are what we call tail latencies.
You got it. Tail latencies are super important.
Okay.
Because they have a disproportionate impact on user experience. Okay. Even if a small percentage of requests are slow, it can make the entire system feel sluggish.
Interesting.
This is especially true for high-value customers or those dealing with large amounts of data.
Okay.
Ensuring fast response times, even for those outlier requests, is crucial.
It's like that saying, you're only as strong as your weakest link.
Exactly.
Now, once you understand the load and performance, what are some approaches to scaling a system to handle growth?
Well, there are two main approaches: scaling up and scaling out.
Okay.
Scaling up, also known as vertical scaling, means getting a bigger, more powerful machine.
Right.
Think of it like upgrading your computer with a faster processor and more memory.
Right.
Scaling out, or horizontal scaling, involves distributing the load across multiple smaller machines.
So it's like choosing between a giant pickup truck and a fleet of smaller delivery vans. Each has its own pros and cons.
Right. Scaling up is often simpler to implement, but there are limits to how powerful a single machine can get.
Right.
You eventually hit a ceiling.
Yeah.
Scaling out provides more flexibility and can handle much larger loads.
Okay.
But it introduces complexity in terms of data consistency and coordination between machines.
Right. So there's no one-size-fits-all solution.
Right.
It depends on the specific application and its needs.
Absolutely. There's no magic scaling sauce that works for every situation.
Makes sense.
The best approach depends on the specific load parameters, the nature of the application, and the trade-offs between simplicity and flexibility.
Right.
Sometimes a combination of scaling up and scaling out might be the best way to go.
Okay. So scalability is all about having strategies to adapt to growth.
Exactly.
But what about the long-term health and management of a system?
Yeah.
That brings us to the concept of maintainability.
Yes. Maintainability is all about making it easy for engineers and operations teams to work with the system over time. It's about minimizing pain during maintenance, whether that's fixing bugs, keeping the system running smoothly, or adapting to new requirements.
Okay.
There are three key principles that contribute to maintainability: operability, simplicity, and evolvability.
Let's break those down. First up, operability.
Sure.
What does that mean in the context of data-intensive systems?
Operability is about making it as smooth as possible for the operations team to keep the system running.
Okay.
This means things like good monitoring tools to track performance and spot problems, clear documentation so everyone understands how things work, and easy-to-use interfaces for managing the system.
So it's about empowering the people who keep things running day to day.
Exactly. The goal is to automate routine tasks and make the system as self-healing as possible.
Okay.
So the operations team can focus on higher-level issues.
That makes sense.
Okay.
What about simplicity?
Yeah.
I can imagine that plays a big role in making a system easier to maintain.
Absolutely. Simplicity is crucial, especially as software projects grow larger and more complex.
Right.
Complexity can really bog down development and make maintenance a nightmare.
I bet.
A key tool for managing complexity is abstraction.
Could you explain what you mean by abstraction?
Sure. Think of it like this. You don't need to know exactly how a car engine works to drive a car, right?
Right.
You interact with the car through a simplified interface.
Right.
The steering wheel, pedals, and gear shift.
Yeah.
The complexity of the engine is hidden from you, making the car easier to operate.
Okay.
Similarly, in software, good abstractions hide unnecessary implementation details.
Right.
Making the system easier to understand and work with.
So it's like creating a clean, well-organized workspace where everything has its place.
Exactly.
Makes it much easier to find what you need and keep things running smoothly.
Yeah.
Now, the final principle, evolvability.
Yes.
It seems particularly important in today's rapidly changing tech world.
It is. Evolvability is all about designing systems that can adapt to new requirements. Okay. And integrate with new technologies as they emerge.
Right.
We want our systems to be flexible and agile enough to handle new use cases, integrate with new platforms, and accommodate evolving business needs.
So it's about future-proofing the system.
Exactly.
Making sure it can gracefully handle whatever changes come its way.
That's a great way to put it. And evolvability is closely tied to simplicity.
Okay.
And good abstractions.
Right.
When a system is easy to understand and its components are well-defined,
yeah,
it's much easier to make changes without unintended consequences.
Right.
It's like building a house with room for expansion.
Yeah.
You plan for future growth from the beginning.
It all comes full circle.
It does.
After this deep dive into reliability, scalability, and maintainability.
Yeah.
I'm curious, what are some key takeaways for our listener who might be building or working with data-intensive applications?
I think the biggest takeaway is that building successful data-intensive applications goes beyond just choosing the right technologies.
Yeah.
It's about understanding those core principles of reliability, scalability, and maintainability, and how they connect to the specific purpose of your application.
Okay.
Like building a bridge requires more than just steel and concrete.
Right.
You have to understand the forces at play and the environment it'll exist in.
Yeah, it's like having a blueprint.
Right.
You need to consider the foundation, the structure, and the long-term plan for growth.
Exactly.
But even with a great blueprint, I imagine there are still challenges along the way.
Oh, absolutely.
Right.
There's no one-size-fits-all solution.
Okay.
Every application has unique requirements and faces its own set of challenges.
Right.
The key is to carefully evaluate the trade-offs.
Yeah.
Learn from others' experiences and continually adapt your design.
So being flexible and willing to learn are key.
Absolutely. The tech landscape is constantly evolving.
Right.
What works today might not be the best solution tomorrow.
Yeah.
It's important to stay curious.
Okay.
Explore new technologies and approaches.
Right.
And be willing to adjust your course as needed.
So it's about being a lifelong learner, isn't it?
It is.
Embracing that journey of discovery and improvement.
Exactly. And being open to collaboration.
Right.
Talk to other developers, read blogs and articles, and participate in online communities.
Yeah.
Sharing knowledge and learning from each other's experiences is crucial.
It's about building a community around these complex challenges.
It is.
This has been an amazing deep dive.
It has.
We've covered so much ground.
Yeah.
What are some things that stood out to you?
You know, for me, it's realizing that even the most complex data-intensive applications rely on these fundamental principles that are surprisingly accessible.
Okay.
Anyone can learn them, even if they don't have a deep technical background.
That's great.
And once you understand these principles, you not only gain a better understanding of the technologies you use every day, but also can make more informed decisions when designing and building your own applications.
Absolutely. It's empowering to go beyond being a passive consumer of technology.
Yes.
And become more active in understanding and even shaping how technology evolves.
Exactly. And it all starts with asking questions, being curious, and seeking a deeper understanding of the systems that power our world.
So to our listener out there, as you continue to engage with technology, keep these principles in mind.
Yes.
Look for those hidden complexities and appreciate the thoughtfulness that goes into creating the systems that makes our lives easier and more connected.
I agree.
That brings us to the end of another deep dive.
Great.
Until next time, keep learning, keep exploring, and keep questioning.